A beam of light left the sun 8 minutes ago. For that beam, 0 time has passed. It left and arrived in the same instant. Right now, on the far edge of the universe, another photon is finishing a journey that began before Earth existed. That trip felt instant too. We're about to follow a single particle of light across billions of miles, through the birth of the universe, past the edge of black holes, and into the strange math that makes clocks disappear. You will meet a twin who ages for years while his brother barely ages at all, travelling close to light speed. You will learn why mass itself is the one thing that keeps every object in the universe from ever catching light. If strange physics gets your brain buzzing, hit like and subscribe before we go. More of this is coming every week. Get ready. We begin now. The light warming your skin right now left the sun 8 minutes ago. It crossed 93 million miles of empty space, the same distance as circling the Earth almost 4,000 times. For you, that trip took 8 minutes and 20 seconds. For the light itself, it took nothing at all. That sentence sounds like a mistake. It is the strangest, best confirmed fact in physics. Here is the mystery hiding inside sunlight. Every second, the sun burns 4 million tons of itself into pure energy, flinging light in every direction at 186,000 miles per second. That speed is fixed. It never changes no matter what pushes it, pulls it, or chases it. According to the light's own experience, if a beam of light could have an experience, it never travels those 93 million miles at all. It leaves and arrives in the same breath. To understand why, picture 2 clocks. One clock sits on your kitchen counter. The other clock rides on the beam of a light leaving the sun. Both clocks tick at the same rate, at least from where you stand. But the closer something gets to light speed, the slower its clock ticks compared to yours. Push that idea all the way to actual light speed, and the clock does not just slow down. It stops. Completely. Forever. This is no rounding error, no quirk of measurement. Physicists have tested it directly. Atomic clocks flown on airplanes tick at different rates than identical clocks left on the ground. Satellites orbiting Earth run their clocks slightly out of step with ours, because they sit farther from Earth's gravity and move at a different speed relative to light. Every test lines up with the same conclusion. Time itself bends around speed. So when sunlight reaches your face, you are touching something that, in its own frame of existence, never moved through time at all. The 8 minutes you experience never happened for it. The 93 million miles you can picture in your head never registered as distance, from the light's own point of view. Now stretch that idea further. The light from the nearest star beyond our Sun, a star called Proxima Centauri, takes over 4 years to reach Earth. For that beam, the 4-year journey is just as instant as the Sun's 8-minute trip. Longer distance, same 0 time. Distance and time stop mattering to something moving at the true speed limit of the universe. This should feel impossible. Speed usually means less time on a clock, not no time. A cheetah crossing a field takes less time than a turtle. A photon crossing a galaxy takes no time at all. Somewhere between the cheetah and the photon, the entire relationship between speed, time, and distance breaks apart and rebuilds into something almost unrecognizable. To understand how that rebuild works, we have to go back nearly 120 years to a 16-year-old boy staring out a window, wondering what it would look like to ride alongside a beam of light. A 16-year-old boy sat in a classroom in Switzerland, half listening to his teacher, running a question through his head that would eventually break physics wide open. What would it look like to ride alongside a beam of light, moving at the exact same speed, and look at another beam next to you? Albert Einstein could not let the question go. If he matched a light beam's speed perfectly, the wave beside him should appear frozen in place, like a photograph of a wave rather than a wave itself. The physics of the time said that was impossible. Light waves could not stand still. A frozen light wave would break every equation describing electricity and magnetism, equations tested again and again without a single failure. For 10 years, Einstein carried that daydream around like a splinter he could not remove. He worked as a patent clerk in Switzerland, examining other people's inventions during the day, chasing his impossible question during the evenings. Most physicists at the time assumed space and time were fixed stages, backgrounds that never changed no matter what happened inside them. Einstein began to suspect the stage itself was bending. In 1905, working mostly alone, he published an answer. Light, he argued, always moves at the same speed for every observer, no matter how fast that observer is moving. A person standing still and a person racing at half the speed of light will both measure the same beam of light moving at the same 186,000 miles per second. That single rule sounds small. It rewired the entire universe. Here is why it mattered so much. Speed is just distance divided by time. If light's speed never changes, and different observers watching the same beam disagree on how far it travelled, then they must also disagree on how much time passed. Time stopped being one universal clock ticking the same for everyone. It became personal, tied to how fast you move. Picture two friends standing on opposite sides of a running track. One friend stays still, the other sprints as fast as a person can run. Watching a lightning bolt strike the finish line, both friends would agree on how fast the light reached their eyes. If the sprinting friend moved close to light speed instead of just running fast, the two friends would start disagreeing about time itself, about how long the bolt took, about which events happened first. Neither friend would be wrong. They would simply be living through different flows of time, stitched together by the one fixed thing in the universe, the speed of light. Einstein's daydream had become a full theory, one that would eventually explain muons raining from the sky, satellites drifting out of sync, and a twin who barely ages while his brother grows old. First, physics needed proof that nothing, absolutely nothing, could catch up to that frozen light wave Einstein once imagined riding beside. Every action movie has a chase scene where the hero almost catches the villain's car. In the real universe, one chase never ends in a catch. Nothing has ever caught light. Nothing ever will. Physicists call the speed of light a cosmic speed limit, but that phrase undersells it. A speed limit on a highway can be broken. A driver can press the pedal down and go faster than the sign allows. The speed of light is not a rule written on a sign. It is baked into the structure of space and time themselves, the same way the number of sides on a triangle is baked into what a triangle is. Here is the strangest part. Reaching light speed does not just get harder, it becomes mathematically impossible for anything with mass. As an object speeds up, it gains what physicists call relativistic mass, extra heaviness that shows up only at extreme speed. The closer an object creeps toward 186,000 miles per second, the heavier it effectively becomes, and the more energy it takes to push it even a little faster. Picture pushing a shopping cart. Empty, it rolls easily. Load it with bricks, and it takes real effort to speed up. Now imagine a cart that gets heavier every single time you push it, no matter how many bricks you add. Near light speed, that is what happens to any object with mass. The energy needed to add more speed climbs toward infinity. An infinite amount of energy does not exist anywhere in the universe, so the object never quite arrives. This is not a limitation of our rockets or our fuel. Even a perfect engine, 100% efficient running on unlimited fuel, would face the same wall. Particle accelerators on Earth have pushed tiny particles to over 99.9% of light speed, using machines miles long and enormous amounts of electricity. Even at that staggering speed, those particles remain just short of the finish line. The last fraction of a percent takes more energy than the rest of the entire race combined. Light gets around this problem in a strange way. Photons, the particles that make up light, have no mass at all. Zero. Nothing to slow down, nothing to grow heavier. Because they carry no mass, the wall that traps every other object in the universe simply does not apply to them. They are the one thing built to travel at the true top speed of reality, and nothing with mass will ever be invited to join them. Scientists have tested this speed limit more than almost any other idea in physics, using particle accelerators, exploding stars, and orbiting satellites. Every test agrees. The speed of light has never been broken, not once, not by accident, not on purpose. The wall itself raises a stranger question. If speed and mass are this tightly locked together, What exactly is time doing to something that has no mass to begin with, something built to never slow down at all? Every clock you have ever trusted has been lying to you a little, not on purpose. It simply could not tell you the full truth because the full truth depends on who is asking. Physicists have a name for the time that ticks on a clock travelling with you, wherever you go. They call it proper time, meaning something closer to your own time, the time your own wristwatch measures as you walk, drive or fly through your day. Here is the twist. Someone else's wristwatch, watching you from a distance while moving at a different speed, will not agree with yours. Not because one watch is broken. Both watches work perfectly. They measure different things. The way a ruler lying flat on a table measures a different length than the same ruler tilted at an angle, even though the ruler itself never changed. Picture a video call with a friend travelling on a rocket close to the speed of light. From your side of the screen, your friend's every movement looks slowed down, like a video buffering. Your friend watching you sees the exact same thing in reverse. You look slow to them. Neither video is buffering. Each of you experiences your own flow of proper time, compared to someone moving differently through space. This sounds like a magic trick, but experiments have confirmed it directly, using tools far more precise than any wristwatch. Scientists have flown atomic clocks on commercial airplanes circling the globe. When those clocks landed and were compared to identical clocks that stayed on the ground, the numbers had shifted by tiny fractions of a second, exactly matching the mathematics. The effect is small at airplane speeds, smaller than a blink, smaller than a heartbeat. It grows the closer an object gets to the speed of light. A spaceship travelling at 90% of light speed would experience time passing at less than half the rate of someone standing still on Earth. A spaceship somehow reaching 99.9% of light speed would experience barely any time at all compared to the people left behind, even as years ticked by back home. This means the universe does not run on one master clock, ticking the same beat for everyone, everywhere. It runs on billions of separate clocks, each one keeping its own proper time, each one perfectly correct for the object carrying it. Your grandmother's kitchen clock, a jet crossing the ocean, and a spacecraft racing toward Mars are all, in a real sense, living in slightly different versions of time. If speed alone can stretch and shrink time this much, one question becomes impossible to avoid. What happens to a photon, an object that does not creep close to light speed, but lives at light speed permanently, every second of its entire existence? Every object you can touch shares one quiet, invisible bill it pays just to exist. That bill is mass, and it buys something you rarely think about, the ability to ever stand still. Photons never pay this bill. They have no mass, and because of that, they cannot slow down, cannot pause, cannot rest even for an instant. The moment a photon exists, it moves at exactly one speed, full speed, forever, until something absorbs it, or it fades into the background of the universe. This sounds backward. Normally, heavier objects seem harder to move, not easier to stop. A bowling ball is harder to push than a tennis ball. At the level of fundamental particles, mass works differently. Mass is not just weight. It is closer to a kind of resistance built into a particle itself, resistance that keeps it from ever reaching the true top speed of the universe. Physicists sometimes describe this using an idea called the Higgs field, an invisible field that fills all of space. Picture a crowded hallway between classes at school. Someone with no friends in the hallway walks straight through without stopping. Someone who has friends everywhere gets stopped constantly, tapped on the shoulder, pulled into conversations, slowed at every turn. The Higgs field acts a little like that hallway. Particles that interact strongly with it get slowed down and gain mass. Particles that barely interact with it, like photons, walk straight through and keep their maximum speed. Because photons carry zero mass, they never experience that hallway slowdown at all. They walk through space at full speed from the instant they are created. A slow photon or a resting photon is not a real thing anywhere in the universe. It is a contradiction, like a square circle. Every object with even a tiny sliver of mass faces the wall from the last chapter. The closer that object pushes toward light speed, the more energy each extra bit of speed demands, climbing toward an amount the universe simply does not have to give. Mass is the toll booth. Pay enough energy, and an object can get closer and closer to the light speed limit. It can never fully arrive because paying the entire toll would require infinite energy. This creates a strange split in the universe. On one side sit massive objects, planets, stars, spaceships, people, forever chasing a speed they can approach but never touch. On the other side sits everything with zero mass, permanently living at the one speed the rest of the universe can only dream about. That split explains why nothing can ever ride beside a photon the way young Einstein once imagined. It raises an even stranger question. If a photon always moves at full speed, with proper time frozen the instant it exists, what does that mean for the photon's own experience of distance itself? Picture the longest trip you can imagine, a rocket crossing the entire galaxy, 100,000 light years from one edge to the other. Now picture a photon making that exact same trip. For the photon, the galaxy is not 100,000 light years wide. It is not wide at all. This is where the earlier chapters collide into something almost too strange to hold in your head at once. A photon's clock is frozen, ticking zero forever. Speeding objects also experience something called length contraction, where distances shrink the faster something travels. Push both ideas all the way to light speed, and distance does not just shrink for a photon. It vanishes completely. From your point of view, standing on Earth, a photon leaving a distant star crosses trillions of miles of empty space, taking thousands or millions of years to arrive. From the photon's own point of view, if it is even fair to say a photon has a point of view, the star and the destination sit at the exact same point, with zero distance between them. It does not travel across the galaxy. In its own frame, it does not travel anywhere at all. Picture folding a giant map in half so that two distant cities touch. From a mile above the map, the cities are still far apart. From the perspective of an ant standing exactly on the fold, the two cities sit right next to each other, distance folded away completely. A photon lives permanently on that fold, at the exact seam where distance collapses to nothing. This idea unsettled physicists for decades because it seems to break basic logic. How can something clearly travel across the universe, arriving billions of years after it left, and also experience no travel at all? Both things are true, just from two different frames. From our frame, the photon absolutely crosses real distance over real time, measured with telescopes and clocks. From the photon's own frame, one that cannot technically be measured the way we measure our own experience, no time and no distance exist to cross. Scientists cannot strap a tiny observer onto a photon and ask it how the trip felt. The mathematics of relativity itself breaks down at exactly light speed, refusing to produce a normal answer to the question of a photon's personal experience. Some physicists argue the question does not even make sense. The same way asking what is north of the North Pole does not make sense. There is no north left to point to. There may be no experience left to describe. Still, the math offers one certainty. Every photon that has ever existed, from the light in your eyes right now to the oldest light in the universe, shares this same frozen relationship with space and time. That shared secret becomes far easier to picture once you meet something with mass that comes close to the same trick. Particles falling from the sky that should not survive their own short lives. High above your head, cosmic rays slam into the top of the Earth's atmosphere every second, smashing air molecules apart hard enough to create brand new particles out of pure energy. Among the particles born in that violent collision are muons, heavier cousins of the electron, and muons should never make it to the ground. They do anyway, by the billions, and the reason why became one of the clearest proofs Einstein ever received. A muon is unstable. The moment it forms high in the atmosphere, a countdown starts. On average, a muon survives only about 2/millionths of a second before falling apart into other particles. 2/millionths of a second sounds impossibly short, and it is. Even travelling near the speed of light, a muon's lifespan should only let it travel about 600 meters, roughly the length of 6 football fields, before it disintegrates. The problem is that muons form roughly 6 miles above the ground, not 6 football fields. Basic math says almost none of them should ever reach sea level. Scientists in the 1940s set up detectors on mountaintops, and again at sea level, to count arriving muons, expecting far fewer at sea level, thinned out by that impossibly short lifespan. Instead, they found nearly the same number of muons at both locations. Something was keeping these particles alive far longer than 2/millionths of a second should allow. The answer was time dilation, the same slowing of clocks we saw with satellites and airplanes, turned up to an extreme. Muons created by cosmic ray collisions move at nearly 99.9% of light speed. At that speed, their internal clock, the invisible timer counting down to their own destruction, runs dramatically slower from our point of view on the ground. A muon's own proper time still lasts only 2/millionths of a second. From our frame, watching it streak downward, that same 2/millionths of a second gets stretched out, giving the muon enough extra time from our perspective to survive the entire 6-mile drop. Picture a firework with an extremely short fuse, timed to fizzle out almost instantly. Now picture that same firework thrown from a speeding truck. To someone standing still, watching the truck race by, the fuse appears to burn in slow motion, giving the firework extra distance before it finally goes off. The fuse itself never changed. Only the outside observer's view of its ticking changed, stretched by speed. This experiment has been repeated many times since the 1940s, using increasingly precise detectors, and the results always agree. Muons genuinely reach the ground because time itself bends around their extreme speed, exactly as Einstein's equations predicted decades before anyone could test it directly. If cosmic rays smashing into our atmosphere can bend time enough to save a doomed particle, a much larger, much more carefully engineered system faces the same bending every day, quietly correcting itself so an entire planet's worth of maps and directions do not fall apart. Every time a phone shows a blue dot moving down a street, a satellite orbiting 12,000 miles overhead is fighting off two separate distortions of time, just to keep that dot accurate. The global positioning system relies on a small fleet of satellites, each one carrying an atomic clock precise enough to lose less than 1 second every few million years. Your phone listens to signals from several satellites at once, comparing the tiny time differences between when each signal left and when it arrived, and calculates exactly where you are standing, often accurate to within a few feet. The entire system depends on satellite clocks staying in perfect sync with clocks on the ground. Relativity says they cannot, not without help. Two effects pull GPS satellite clocks in opposite directions. First, the satellites orbit at roughly 9,000 miles per hour, fast enough for time dilation from speed to kick in. The same effect that slowed the muons in the airplane clocks. Moving that fast, a satellite's clock runs slightly slower than a clock sitting still on Earth, losing about 7 microseconds every day. Second, gravity itself bends time. GPS satellites orbit far above most of Earth's gravity, in a weaker gravitational pull than we feel on the surface. Weaker gravity means time runs faster, not slower. This gravitational effect adds about 45 microseconds per day, pulling the satellite clocks ahead. Add both effects together, and GPS satellite clocks run about 38 microseconds faster per day than identical clocks on the ground. 38 microseconds sounds impossibly tiny. Less than the blink of an eye repeated 1,000 times. GPS calculates your position using the speed of light, roughly 1 foot per nanosecond. A drift of 38 microseconds, left uncorrected, would create a positioning error of about 7 miles, growing worse every single day. Picture a marching band trying to stay in step while several drummers secretly play at slightly different tempos. Within a few measures, the band would fall apart, feet landing at different times, the performance collapsing into noise. GPS engineers solved this problem before it ever became noise, building the relativistic time correction directly into each satellite before launch, deliberately making the onboard clocks tick slightly slower than normal, so that once they reach orbit and speed up, gravity and motion balance out to match clocks on Earth. Every direction your phone has ever given you, every blue dot tracking your walk down a street, exists because engineers accounted for Einstein's equations on purpose. Skip that correction, and GPS would become useless within a single day. If satellites need this kind of correction, just orbiting a few thousand miles above Earth, something far more dramatic happens to time for anyone who leaves the planet entirely, racing towards space at speeds no satellite has ever reached. astronaut Scott Kelly spent 340 days aboard the International Space Station, circling Earth at roughly 17,000 miles per hour. When he came home, he had aged slightly less than his identical twin brother Mark, who stayed on the ground the entire time. The difference measured only a few milliseconds, but it was real, measurable, and exactly what physics predicted. This might sound like a contradiction of the GPS chapter, where weaker gravity made clocks run faster. The difference comes down to altitude. The International Space Station orbits only about 250 miles above Earth, far lower than GPS satellites, which sit around 12,000 miles up. At that lower altitude, the speed effect from orbiting so fast wins out over the gravity effect from being slightly farther from Earth. The result flips compared to GPS. Astronauts on the space station experience time running slightly slower than people on the ground. Scott and Mark Kelly became one of the most famous natural experiments in relativity because NASA had a rare opportunity, comparing two people who share identical genetics, one who stayed on Earth and one who left it. Researchers studied Scott's body extensively after his return, tracking hundreds of biological changes caused mostly by the extreme environment of space, radiation, isolation, lack of gravity. Buried inside that mountain of data was a separate, much smaller effect that had nothing to do with biology at all. Scott's body had genuinely travelled through slightly less time than his brother's, purely from moving fast enough for long enough to matter. Picture two friends leaving a party at the exact same moment, one walking home along the sidewalk, the other jogging around the block first before arriving home later. The jogger did not experience the walk home differently in any meaningful sense. The jogger's watch would show the same time as the walker's, because walking speed barely registers on the relativity scale at all. Now imagine the jogger circling the block at 17,000 miles per hour instead. At that speed, the jogger's watch genuinely falls a tiny bit behind, even though both friends still end up standing in the same kitchen at the end of the night. Scott Kelly's mission produced a time difference of roughly 5 milliseconds compared to his brother, an amount smaller than the blink of an eye, smaller than the time it takes a fly to flap its wings once. Small as it was, the number matched Einstein's equations almost perfectly, calculated in advance before Scott ever left the ground. This tiny gap between two brothers hints at something far larger waiting at more extreme speeds. If 340 days in low orbit created a measurable time difference, what would happen to a person who spent years, not days, travelling at speeds far closer to light itself, leaving someone they love behind on Earth? Imagine two twins standing on a launch pad saying goodbye. One twin boards a spaceship bound for a star 20 light-years away, travelling at 99% of the speed of light. The other twin stays home watching the sky, waiting. The travelling twin reaches the star, turns the ship around and comes home. From the perspective of the twin who stayed on Earth, the whole round trip takes a little over 40 years, since light itself would need 40 years to make that round trip, and the ship moves almost as fast as light. For the twin aboard the ship, thanks to time dilation at 99% of light speed, the entire journey feels like only about 6 years have passed. The twins reunite. One has aged 6 years, the other has aged over 40. Same starting moment, same reunion, two wildly different amounts of time experienced in between. Physicists call this the twin paradox, though it is not actually a paradox once you understand why it happens. It is one of the most solid, well-tested predictions relativity ever made. For decades after Einstein first published his ideas, critics tried to poke a hole in this scenario. If motion is relative, they argued, couldn't the travelling twin just as easily claim they stayed still while the Earth and the stay-home twin rocketed away instead? Shouldn't both twins age the same amount? The hole in that argument comes down to one crucial difference between the twins. The Earthbound twin never changes speed or direction throughout the entire story. The travelling twin does. Reaching the distant star requires slowing down, turning the ship around and accelerating back toward home. That acceleration breaks the symmetry between the two twins completely. Only the travelling twin experiences the forces of speeding up and slowing down, and only the travelling twin's clock ends up genuinely measurably behind. Picture two people leaving the same starting line on a running track, one jogging in a straight line for a mile, the other running the same distance but weaving back and forth across the lanes the entire way. Even though both cover the same straight line distance eventually, The weaving runner's path adds up to more total distance covered. The travelling twins' path through space-time works the same way. Their journey, bending and curving through both space and time, adds up differently than a straight, steady path through time alone. No human twins have made this exact trip yet, since no spacecraft can currently reach anywhere near 99% of light speed. Every piece of this story has already been tested separately through muons, GPS satellites, and astronauts like Scott Kelly. Scientists trust the twin paradox completely, because every smaller version of it has already come true. If speed alone can stretch a twin's youth across decades, an entirely separate distortion of the universe waits just ahead, one that squeezes and flattens objects instead of stretching their time. A spaceship racing past Earth at 90% of light speed would look strange to anyone watching from the ground, not because of anything happening to its engines or its crew, but because the ship itself would appear flattened, squeezed shorter along the direction it travels, like a photograph stretched the wrong way and then squashed back down. This effect is called length contraction, the twin sibling of time dilation. The two effects always show up together, born from the exact same source, the fixed, unbreakable speed of light. If time can stretch and slow depending on how fast something moves, distance has to bend along with it, or the universe's math would stop balancing. Physicists describe it this way: an object moving close to light speed, viewed from outside, measures shorter along its direction of travel than the same object measured while sitting still. A 100-meter spaceship travelling at 90% of light speed would measure only about 44 meters long to someone watching it fly past. The ship's crew, sitting inside, would notice nothing unusual about their own ship at all. To them, everything on board looks completely normal. The contraction only shows up from an outside point of view, watching something else move. This is not an optical illusion, the way a stick looks bent when it enters water. Length contraction is a real change in how much space an object occupies, agreed upon by anyone measuring it from outside that object's frame of motion. Particle accelerators provide constant proof. When physicists smash particles together at speeds extremely close to light, the particles behave as though they have been squashed nearly flat along their direction of travel, exactly matching the contraction predicted by the equations, confirmed over and over in facilities like the ones at CERN in Switzerland. Picture a slinky toy stretched out along a hallway. Someone at the far end of the hallway grabs it and yanks it toward themselves extremely fast. From the perspective of someone standing to the side watching the whole hallway, the slinky briefly appears to bunch up and shorten as it races past, even though nothing about the slinky's actual coils has permanently changed. Length contraction works a little like that snapshot, a genuine shortening that depends entirely on your point of view and how fast the object moves relative to you. Push length contraction all the way to its extreme, exactly to light speed itself, and something remarkable happens. The contraction does not just shrink an object a little, it shrinks distance itself down to nothing. This is the missing piece connecting everything we have covered so far. A photon experiences zero length between any 2 points, because at its permanent, unchanging speed, length contraction has flattened all distance completely away. Time freezes for a photon, distance vanishes for a photon. Both effects trace back to the exact same speed, the exact same limit, the one number the entire universe seems to organize itself around. That same organizing number governed one of the oldest events the universe has ever produced, a burst of light released nearly 14 billion years ago that is still arriving today, carrying a message from the very beginning of everything. Point a specialized telescope at any patch of empty-looking sky, and it will pick up a faint, steady hiss of radiation, arriving equally from every direction, every second. That radiation is the oldest light in the universe, and it has been travelling toward every telescope on Earth for nearly 14 billion years. Scientists call it the cosmic microwave background. In the earliest moments after the Big Bang, the universe was an unimaginably hot, dense soup of particles, so tightly packed together that light could not travel freely at all. Photons kept slamming into charged particles almost the instant they were released, bouncing around chaotically instead of streaming outward the way sunlight does today. The early universe was, in a real sense, foggy, opaque. impossible to see through. That fog lifted about 400,000 years after the Big Bang, when the universe had expanded and cooled enough for electrons to finally settle into orbits around atomic nuclei, forming the first stable atoms. The instant that happened, space cleared. Photons that had been trapped, bouncing endlessly, suddenly found nothing left to block their path. They shot outward freely in every direction, and they have been travelling ever since. That single burst of light, released the moment the universe first became transparent, is the cosmic microwave background detected today. Every photon in it has been flying through space, uninterrupted for nearly 14 billion years, making it the oldest light any instrument on Earth has ever captured. Picture a massive fog bank finally clearing over a valley at dawn. The instant the fog lifts, sunlight that had been scattered and blocked suddenly races unobstructed toward every rooftop, every window, every eye looking up. The cosmic microwave background is that same kind of release, happening once, at the very beginning of time, on a scale spanning the entire universe instead of a single valley. Scientists first detected this ancient light by accident in 1965, when two researchers at Bell Labs kept picking up a strange, unexplainable hiss of radiation with a radio antenna, no matter which direction they pointed it. They initially suspected pigeon droppings inside the antenna, or faulty equipment. Neither explanation held up. The hiss was real, and it matched almost perfectly what physicists had separately predicted should exist if the Big Bang theory was correct, a discovery that helped cement the Big Bang as the leading explanation for how the universe began. Since then, satellites have mapped this ancient light in extraordinary detail, revealing tiny temperature differences across the sky, differences smaller than a fraction of a degree that mark the seeds of every galaxy, star, and planet that would eventually form. This light has been travelling for nearly the entire age of the universe. Thanks to everything we now understand about time and speed, that impossibly long journey carries a strange twist for the photons themselves, one that connects directly back to the frozen clocks we uncovered several chapters ago. The cosmic microwave background has been crossing the universe for nearly 14 billion years. From its own frame, if that phrase means anything at all for something built entirely of light, not a single second of that journey ever happened. This connects directly back to a truth from earlier in this story. Every photon, no matter how far it travels, or how long that journey takes according to outside observers, experiences zero proper time and zero distance. The cosmic microwave background is simply the most extreme example of this rule that exists anywhere in the universe. Its photons left the moment the universe first became transparent, and in a real sense, from their own frozen relationship with time, they have not aged a single instant since. Astronomers sometimes describe this ancient light as a fossil, and the comparison fits better than it might first seem. A fossil preserves a snapshot of something ancient, frozen in a form that lets scientists study conditions from millions of years ago without needing a time machine. The cosmic microwave background works the same way, preserving an exact snapshot of the universe as it existed 400,000 years after the Big Bang, carried forward untouched, arriving today exactly as it left. There is a difference between a fossil buried in rock and this fossil made of light. A dinosaur bone changes as it fossilizes, minerals slowly replacing its original material over millions of years. This ancient light has changed too, though not through time passing for the photons themselves. The universe's own expansion has stretched the light along the way, a separate effect we explore next called redshift. Picture a photograph taken the instant a fireworks show begins, capturing the very first spark before anything else happens. That photograph, if it somehow kept travelling through the air itself instead of sitting in a frame on a wall, would still show that exact first spark no matter how many years passed before someone finally looked at it. The cosmic microwave background is that photograph, endlessly moving, endlessly preserving its first captured instant, arriving fresh every time a telescope finally catches it. Because these photons carry zero proper time, they represent something almost impossible to fully picture. They are in the truest sense physically ancient, having existed since almost the beginning of everything, while simultaneously experiencing no aging process at all in their own frame. The oldest objects science has ever detected are also, from their own frozen relationship with time, the youngest thing possible, existing in a permanent unaging instant. This paradox only deepens once you notice what billions of years of travel through an expanding universe actually do to a photon's appearance. Even while its internal clock stays locked at zero, that stretching effect turns brilliant, high-energy light from the early universe into the faint microwave hiss detected today, a transformation with its own name and its own strange story. The cosmic microwave background did not start out as microwaves at all. When it first burst free across the young universe, it existed as visible light, roughly as bright and energetic as the glow inside a very hot oven. Today, after travelling for nearly 14 billion years, it arrives as a faint microwave hiss, barely detectable, its energy stretched down to almost nothing. The universe itself did that stretching, through a process called redshift. Redshift happens because the universe is expanding, growing larger every moment, carrying galaxies farther apart from each other even as you read this sentence. Light travelling through that expanding space gets stretched along with it, the same way a drawing on a balloon stretches and distorts as you blow more air inside. A wave of light that started with tightly packed peaks and troughs ends up with peaks and troughs spread farther apart, and that stretching changes the light's colour. Light with tightly packed waves carries high energy and appears blue or violet. Light with widely spread waves carries lower energy and appears red, or beyond red entirely, sliding into infrared, then microwaves, then radio waves. As the universe expanded over billions of years, the cosmic microwave background's waves stretched further and further, sliding the light's colour steadily downward until it landed in the microwave range detected today. Astronomers use this same effect on a smaller scale to measure how far away distant galaxies sit. A galaxy racing away from Earth, carried by the universe's expansion, stretches its light toward the red end of the spectrum. The faster a galaxy appears to move away, and the farther it sits, the more dramatically its light shifts toward red. By measuring exactly how much a galaxy's light has redshifted, astronomers calculate distances across billions of light years, reading the universe's own stretch marks. Picture a rubber band with evenly spaced marker lines drawn across it. Stretch that rubber band, and the marks spread farther apart, though none of the marks themselves change shape or size. Light waves crossing an expanding universe behave the same way, their wavelength quietly stretching apart over billions of years of travel, even though nothing about the original light wave broke or malfunctioned along the way. The ancient light detected today is not a perfect, unchanged copy of what left the early universe. Its colour has transformed dramatically, shifted by the space it crossed rather than by anything happening to the photons themselves in their own frozen frame of time. The photon's internal clock never ticked. Its colour still changed completely, stretched by a universe that kept growing underneath it the entire journey. Redshift proves the universe is expanding, and expanding space bends light in ways gentle enough to study from any rooftop with the right equipment. Gravity, when concentrated into something extreme enough, bends both light and time far more violently, pulling both toward a place where the ordinary rules finally break down entirely. Drop a clock toward a black hole, and something happens that no amount of speed alone could ever cause. The clock does not just slow down. From far enough away, watching it fall, the clock appears to freeze completely, stuck forever at the exact edge of the point of no return. Black holes form when massive stars collapse in on themselves, crushing an enormous amount of matter into an incredibly small space. The result is gravity so extreme that it warps the space and time around it dramatically, far beyond anything experienced anywhere else in the universe. The boundary marking the edge of a black hole is called the event horizon, marking the point where gravity's pull becomes so strong that nothing, not even light, can escape back out. Gravity bends time even outside a black hole, an effect we touched on briefly with GPS satellites, where weaker gravity in orbit made clocks run slightly faster than clocks on Earth's surface. Near a black hole, that same gravitational time dilation gets pushed to an extreme, The closer an object gets to the event horizon, the slower its clock runs compared to someone watching from a safe distance. Picture two friends, one standing near a black hole's event horizon in a specially shielded spaceship, the other watching from far away through a telescope. From the distant friend's point of view, the friend near the black hole appears to move in slower and slower motion the closer they drift toward the edge, their clock ticking down toward a near standstill. From the perspective of the friend near the black hole, nothing feels unusual at all. Their own wristwatch keeps ticking normally, their own thoughts flow at a completely ordinary pace. Time only appears frozen from the outside, watching someone else approach the edge. This creates a strange, almost unsettling picture. If you watched a friend fall toward a black hole, you would never actually see them cross the event horizon, not within any amount of time you could wait. Their image would appear to slow down more and more, growing dimmer and more stretched out, approaching the edge forever without ever quite seeming to reach it, at least from your outside point of view. From their own perspective, they would cross the event horizon in a completely ordinary, unremarkable amount of time, based on their own wristwatch. Scientists have confirmed gravitational time dilation using far gentler tests than actual black holes, including experiments comparing clocks at different heights on Earth, since even a small difference in altitude changes the strength of gravity pulling on each clock. Every test agrees with the mathematics precisely, giving scientists confidence that the extreme version, happening at the edge of a black hole, follows the exact same rules, just amplified almost beyond imagination. Time freezing near a black hole's edge raises an even stranger question about light itself. If gravity can trap something moving at the one true speed limit of the universe, an object built to never slow down or stop, what exactly happens the moment light crosses that final, fatal boundary? Light has never lost a race in the history of the universe. At the edge of a black hole, light loses anyway, not by slowing down, but by running out of room to run at all. A black hole's gravity grows so intense near its center that the fabric of space itself gets pulled inward, almost like a whirlpool spiraling toward a drain. Past a certain boundary, the event horizon we met last chapter, every possible direction, forward, backward, sideways, all point inward toward the black hole's center. Escaping stops being a matter of speed. It becomes a matter of geometry, and inside the event horizon, geometry itself no longer offers an outward path. Picture a river flowing toward a massive waterfall, moving faster and faster the closer it gets to the edge. A fish can swim upstream easily in calm water, moving faster than the gentle current pushing against it. Past a certain point near the waterfall, the current itself moves faster than any fish could ever swim, no matter how strong or fast that fish becomes. The fish is not too slow. The river itself has outraced every possible fish. Space near a black hole's event horizon works the same way, flowing inward faster than even light. The fastest thing in the universe can push back outward. This explains why black holes appear completely black, hiding everything that falls past their edge. Light does not need to be caught or trapped by some outside force, the way a fly gets caught in a spider's web. Light simply has no outward direction left to travel in once it crosses that boundary. Every path light could take curves back toward the center instead of away from it. Scientists first predicted this outcome using Einstein's equations decades before anyone had direct evidence that black holes were real, rather than just a strange mathematical possibility. Confirmation came gradually, through indirect evidence like stars orbiting an invisible, incredibly massive object at the center of our own galaxy, and then dramatically in 2019, when an international team of astronomers released the first ever direct image of a black hole's silhouette, captured using a network of telescopes spanning the entire planet, working together as one enormous instrument. That image showed exactly what the mathematics predicted: a dark, perfectly round shadow surrounded by a glowing ring of superheated gas, light bending sharply around the black hole's extreme gravity before either escaping outward or vanishing across the event horizon forever. The universe's fastest, most unstoppable traveller, the one thing built to never be caught by anything else, meets its only true match at the edge of a black hole, through a place where every direction simply stops leading outward. If gravity this extreme can trap even light itself, gentler versions of that same gravity are quietly bending time all around us, all the time, in places far less dramatic than a black hole's crushing edge. Right now, a clock sitting in your basement is ticking very slightly slower than a clock sitting in your attic. The difference is far too small for any wristwatch to notice, but it is real, measured and confirmed, and it comes entirely from a difference in gravity between two floors of the same house. This effect, called gravitational time dilation, follows a simple rule. The stronger the gravity pulling on a clock, the slower that clock ticks compared to a clock sitting somewhere with weaker gravity. Your basement sits slightly closer to the centre of Earth's mass than your attic, meaning it experiences a tiny bit more gravitational pull and a tiny bit slower flow of time. This might sound too small to matter, but scientists have measured it directly, using clocks separated by height differences as small as a single foot. In one especially precise experiment, researchers placed atomic clocks on shelves just slightly different heights apart, and detected the resulting time difference clearly, confirming that gravity bends time at scales far smaller than a mountain or a satellite's orbit, small enough to matter between a countertop and a shelf above it. Picture a heavy bowling ball resting on a stretched trampoline, creating a deep dip in the fabric around it. Marbles rolled near the bowling ball curve inward, pulled by the dip, the same way planets curve around the sun's gravity. Einstein's equations describe gravity working almost exactly this way, except the trampoline is not just space. It is space-time itself, meaning the dip caused by a massive object bends time along with space. Closer to the bowling ball, where the dip is steepest, time runs slower. Farther away, where the trampoline stays flatter, time runs closer to normal. This same effect explains why GPS satellites needed that gravitational correction from several chapters ago, running faster than clocks on the ground because they orbit farther from Earth's gravitational pull. It explains why astronauts on the International Space Station experience a competing pull between their high speed, which slows their clocks, and their moderate altitude, which speeds their clocks back up slightly, though not enough to cancel out the speed effect entirely. Pushed to its most extreme version, gravitational time dilation becomes the frozen clock waiting at the edge of a black hole, the point where gravity grows so strong that time itself appears to stop entirely from an outside point of view. Every version of this effect, from a basement clock to a black hole's edge, follows the exact same mathematics, just scaled to wildly different intensities. Gravity and speed, two completely different things, both bend time in measurable, predictable ways, confirmed from mountaintops, airplanes, satellites, and now black hole silhouettes captured by telescopes spanning the entire planet. Two separate forces, one shared result, time itself refusing to run at the same rate anywhere in the universe. With gravity and speed both capable of bending time this dramatically, one number ties every example in this story together. A single value that grows without limit as speed approaches light itself, a number physicists call the Lorentz factor. Every time dilation number in this story, from muons to GPS satellites to astronauts, traces back to one single equation, a small but powerful formula physicists call the Lorentz factor. Learn this one number, and every strange effect in this story suddenly clicks into a single, unified picture. The Lorentz factor answers a simple question: how much does time stretch and length shrink for an object moving at a given speed compared to something standing still? At everyday speeds, walking, driving, even flying in a jet, the Lorentz factor sits so close to the number 1 that its effects vanish into rounding errors, far too small for human senses to notice. Push speed higher toward a meaningful fraction of light speed, and the number starts climbing, slowly at first, then faster, then explosively. At half the speed of light, the Lorentz factor sits at about 1.15, meaning time stretches by only 15%, barely noticeable without precise instruments. At 90% of light speed, the number jumps to about 2.3, meaning a clock moving that fast runs at less than half the rate of a stationary clock. At 99% of light speed, the number rockets to about 7. At 99.9%, it reaches roughly 22. Each tiny step closer to light speed produces a dramatically larger jump in the Lorentz factor than the step before it. Picture pressing the gas pedal in a car that behaves strangely. For the first 90 miles per hour, the speedometer climbs normally, smoothly, predictably. Past 90 miles per hour, each additional mile per hour suddenly demands enormously more effort than the last, and the cars inside start behaving more and more strangely the harder you push. The Lorentz factor works like an invisible speedometer for reality itself, calm and gentle at low speeds, wild and explosive as speed creeps toward its absolute limit. At exactly light speed, this number stops being a number at all. Mathematically, it approaches infinity, meaning time would need to stretch infinitely, length would need to shrink infinitely, just to keep the equations balanced. Physicists read that infinite result as proof, not as a loophole. Nothing with mass can ever fully reach light speed, because doing so would require an infinite amount of energy, matching the infinite value the Lorentz factor produces at that exact point. Photons sidestep this entire explosive climb, because they never experience the climb from the middle of the graph the way a spaceship would. They are born already living at the one speed where the Lorentz factor stops being a finite number altogether, existing permanently at the edge the equation itself cannot fully describe. This single formula explains muons surviving their fall through the atmosphere, astronauts aging slightly less than people on the ground, and the impossible wall separating everything with mass from everything without it. One number, climbing from one toward infinity, quietly running the entire universe's relationship with time. If this number explains why nothing with mass can catch light, it also explains something even stranger. Why nothing, not even an observer riding beside a photon in their imagination the way Einstein once pictured, could ever actually watch light travel at all. Einstein's teenage daydream, chasing a beam of light and watching it frozen beside him, turns out to be more than just difficult. According to his own later equations, the scenario is not simply hard to achieve. It cannot exist in the universe at all, for reasons buried directly inside the Lorentz factor from the last chapter. To ride alongside a photon, matching its speed exactly, an observer would need to reach the speed of light themselves. The wall from Chapter 3 blocks that outcome completely for anyone or anything carrying mass. As speed approaches light speed, the energy required to keep accelerating climbs toward infinity, and no source of energy in the universe, however large, can ever supply an infinite amount. The observer never arrives at the speed needed to match the photon's pace no matter how close they get. Even setting energy aside, the Lorentz factor breaks down completely at exactly light speed. Plugging light speed directly into the equation produces a division by zero, a mathematical dead end rather than a real usable number. Physics equations hitting a wall like this usually signal something deeper than a calculation error. They signal that the scenario itself does not fit inside the rules of the universe. Picture trying to draw a map that shows what lies north of the North Pole. Every direction on Earth eventually points south once you stand exactly at the pole. North simply runs out of meaning at that exact point. Asking what an observer moving alongside a photon would see runs into the same kind of dead end. A question built on a frame of reference that the universe itself refuses to provide. This means Einstein's own daydream, the spark that launched his entire theory, turned out to describe something his finished theory proved could never actually happen. Riding beside light is not merely difficult, the way climbing an extremely tall mountain is difficult. It sits entirely outside what the universe allows for anything with mass, a boundary as absolute as the Lorentz factor's climb toward infinity. Physicists sometimes call this the ultimate speed limit's built-in protection, a kind of cosmic safeguard preventing paradoxes and contradictions that riding beside a photon would create. If an observer could match a photon's pace exactly, they would need to watch a frozen light wave, exactly like young Einstein once imagined, an outcome that would break Maxwell's equations describing how electricity and magnetism behave, equations tested with extraordinary precision for over a century without a single failure. The universe seems to protect itself from this contradiction by making the matching speed permanently unreachable for anything with mass, keeping light's wave nature intact for every possible observer who could ever exist. Not everything with mass sits equally far from this limit. Somewhere between ordinary matter and massless light exists a strange, nearly weightless particle that comes closer to light speed than almost anything else in the universe, slipping through entire planets without ever being noticed. Right now, trillions of ghostly particles called neutrinos are streaming through your body, through the walls of your house, through the entire planet beneath your feet, and you will never feel a single one. Most neutrinos pass completely through the Earth without hitting a single atom along the way, slipping through solid rock the way sunlight slips through a clean window. Neutrinos come from nuclear reactions born inside the Sun, inside exploding stars and inside particle collisions here on Earth. For decades, scientists believed neutrinos carried no mass at all, exactly like photons, making them a second kind of particle permanently locked at light speed. Careful experiments eventually proved that assumption wrong. Neutrinos do carry a tiny amount of mass, so small that scientists still have not measured its exact value precisely, only that it exists and sits far below the mass of nearly every other known particle. Because neutrinos carry mass, they cannot reach the true speed of light. They come remarkably close. Neutrinos produced in violent cosmic events travel at speeds so near light speed that the difference becomes almost impossible to measure directly, requiring some of the most sensitive detectors ever built by scientists. Picture a runner so fast that photographs from a finish line camera struggle to prove they crossed even a fraction of a second behind the actual light speed limit itself. Neutrinos run that race constantly, losing by margins so razor-thin that only extraordinarily precise instruments can detect the gap at all. One especially dramatic piece of evidence came from a supernova explosion detected in 1987, a massive star tearing itself apart in a galaxy neighbouring our own. That explosion released both light and neutrinos at essentially the same moment. Neutrinos, despite passing through the exploding star's dense material almost instantly, arrived at Earth's detectors a few hours before the visible light from the explosion did, because light took longer fighting its way out through the star's own thick outer layers. Once both signals reached open space, they travelled the remaining distance to Earth at nearly identical speeds, confirming that neutrinos, while not quite reaching light speed, come astonishingly close. Because neutrinos carry mass, even an extremely tiny amount, the Lorentz factor still applies to them, just pushed to an extreme most particles never reach. A neutrino moving at nearly light speed experiences time passing dramatically slower than an outside observer would measure, though never fully freezing the way a true photon's time freezes completely. Neutrinos occupy a strange middle ground, close enough to light speed to feel almost like massless travellers, yet permanently barred from ever fully joining photons at the true edge of the universe's speed limit. That gap, tiny as it is, marks the difference between almost touching zero proper time and actually living there permanently, a distinction that belongs to only one category of particle in the entire universe. Every photon that has ever existed, from the light bouncing off this very sentence into your eyes to the oldest microwave radiation left over from the beginning of everything, shares one identical, unbreakable relationship with time. None of them have ever aged, none of them ever will. This connects every idea from this story into a single thread. Photons carry zero mass, so the energy wall that traps everything else in the universe never applies to them. They travel permanently at the one true speed limit, so their Lorentz factor sits at infinity, collapsing their proper time down to exactly zero and their experienced distance down to exactly nothing. Every photon, everywhere, at every moment since the universe began, exists inside that exact same frozen relationship. This creates a strange kind of universal sameness across every beam of light imaginable. A photon released from a candle flame in your living room shares this frozen relationship with a photon released from a star exploding on the far side of the universe. A photon reflecting off your bathroom mirror this morning shares it with a photon that left the cosmic microwave background nearly 14 billion years ago. Different origins, different journeys, different colours, different energies, and yet every single one experiences the exact same zero passage of time. Picture every photon in the universe as a runner competing in a race with only one possible finish time, regardless of how long the racetrack happens to be. A sprinter running 100 meters and a marathon runner covering 26 miles would normally finish at wildly different times. Every photon finishes its own race, however short or impossibly long that race appears to outside observers, in exactly the same zero amount of time according to its own internal clock. This uniform relationship holds regardless of a photon's energy, color, or origin. A high-energy gamma ray blasted out during a distant star's explosion and a low-energy radio wave humming quietly from your favorite radio station both share this identical zero proper time relationship, despite carrying wildly different amounts of energy. Energy and color change how a photon interacts with matter and how it appears to instruments and eyes. They never change its fundamental relationship with time itself, locked permanently at zero the instant any photon comes into existence. This shared frozen relationship means every photon detected by every telescope, every eye, every camera throughout all of human history has, in its own experience, never aged a single moment between its creation and its arrival, no matter the distance, no matter the years that passed for everyone watching from outside. If every photon shares this exact same frozen relationship with time, one more question becomes impossible to avoid. What actually happens in the single instant a photon comes into existence, and in the single instant it finally strikes something and disappears forever? A photon lives an entire existence, from birth to death, without a single tick of time passing on its own internal clock. From outside, watching a photon leave a star and finally land on a telescope sensor years or centuries later, that entire journey unfolds across a real, measurable stretch of time. From the photon's own frozen frame, birth and death happen as a single unbroken instant, with nothing in between. A photon's birth typically happens through some kind of energy release. An electron inside an atom drops from a higher energy level to a lower one, releasing the extra energy as a photon of light. A nuclear reaction inside the sun fuses hydrogen into helium, releasing photons as a byproduct of that fusion. A star's core collapses violently, releasing a sudden burst of high-energy photons across the electromagnetic spectrum. In every case, energy converts into light in one instantaneous event, a photon springing into existence already moving at full speed, with no gradual startup or acceleration required. A photon's death happens the same way in reverse, absorption instead of creation. When a photon strikes an atom, its energy can knock an electron up to a higher energy level, or heat up a surface, or trigger a chemical reaction inside a camera sensor or the back of an eye. The instant that absorption happens, the photon stops existing as a photon at all, its entire energy transferred completely into whatever absorbed it. Picture a single word shouted across an empty canyon. The moment the word leaves your mouth, and the moment it fades into silence on the far canyon wall, might be separated by several seconds from your point of view standing at the canyon's edge. If you somehow experienced that echo's journey from the inside, riding along with the sound itself rather than watching it travel, the shout and its fading would happen as one single unified event, with no meaningful gap between them. A photon's birth and death work this way, though far more extreme, collapsing an entire journey across a galaxy into a single instant from its own impossible point of view. This means a photon never experiences existing partway through its trip. It does not experience floating quietly through empty space, drifting for years the way a boat drifts across an ocean. Birth and death sit directly next to each other in its own frame, with the entire outside journey, however many billions of miles long, squeezed into a single unbroken moment. Outside, observers see something completely different, a photon genuinely crossing real distance over real time, sometimes billions of years of it, carrying real information about the star or event that created it. Both descriptions are correct, simply describing the exact same event from two frames that can never fully agree on how long anything actually took. This single instant birth and death raises one final, stranger question about the photon's experience along the way. If a photon experiences no time and no journey, what happened to the distance itself, the billions of miles that so clearly separate a distant star from the telescope, finally capturing its light? A star sits 4 billion light-years from Earth. A telescope on a mountaintop finally captures one of its photons tonight. From Earth's point of view, that photon crossed 4 billion light-years of real, measurable space. From the photon's own point of view, it crossed no distance at all, because from a photon's frame, distance itself does not exist as we understand it on Earth. This circles back to the length contraction we uncovered several chapters ago, pushed to its absolute, most extreme limit. Any object moving close to light speed measures shorter distances along its direction of travel than a stationary observer would measure for that same trip. A photon moves at exactly light speed, not close to it, so this shrinking effect reaches its maximum possible strength. Every distance a photon could ever cross, whether a few feet across a room or 4 billion light-years across the visible universe, contracts down to exactly zero in the photon's own frame. This does not mean the photon perceives itself standing still, or perceives some tiny remaining sliver of distance. Zero means zero. The star that released the photon and the telescope that finally captures it exist from the photon's frame at the exact same point in space, connected by no meaningful gap whatsoever. Picture folding an enormous strip of paper representing that 4 billion light-year journey, folding it over and over until the two ends touch directly. From above, looking down at the folded paper, someone could trace a finger from one end to the other in a single motion, feeling no real distance between the 2 points at all, even though unfolding that same paper would reveal an enormous length stretched out across the table. A photon lives permanently in that folded state, the star and the telescope pressed directly against each other in its own experience, even while the unfolded version spans billions of light-years for everyone else. This creates one of the strangest conclusions in this entire story. Space and distance, concepts that feel as solid and unquestionable as anything in daily life, turn out to depend entirely on how fast the thing measuring them happens to be moving. For a person walking down a street, distance behaves normally, exactly as expected. For a photon, distance stops existing altogether, collapsed completely by a speed the rest of the universe can only approach and never fully reach. Scientists cannot place an observer directly inside a photon's frame to confirm this experience firsthand, since the mathematics of relativity breaks down at exactly light speed rather than producing a clean describable answer. Every indirect test, every experiment on length contraction at speeds just short of light speed, points toward this same conclusion as the natural, unavoidable endpoint. If nothing with mass can ever fully reach this zero distance, zero time state, a natural question follows. Could anything, even something purely theoretical, exist on the other side of light speed entirely, moving faster rather than merely approaching it? Somewhere in the outer edges of theoretical physics lives an imagined particle called a tachyon, a particle that would always move faster than light, never slower, permanently trapped on the opposite side of the universe's speed limit the way ordinary matter stays trapped below it. The idea sounds like a loophole at first. If ordinary particles can approach light speed but never quite reach it, and photons live exactly at light speed permanently, perhaps something else could exist permanently above light speed instead, never needing to cross the impossible barrier in the middle at all. Tachyons, if they existed, would work exactly this way, starting faster than light and staying there, the same way photons start at light speed and stay there. The mathematics describing tachyons produces deeply strange results. A tachyon's mass, plugged into the same equations governing ordinary matter, would need to be what physicists call imaginary, a mathematical concept involving the square root of a negative number, something that does not correspond to any measurable physical property. Even stranger, as a tachyon gained energy, it would need to move faster, not slower, and as its energy dropped towards zero, its speed would need to climb toward infinity instead of slowing to a stop. Picture a car with a gas pedal wired backward, where pressing down slows the car and easing off speeds it up endlessly. Nothing in ordinary experience behaves this way, and nothing measured directly in any laboratory experiment has ever behaved this way either. Tachyons remain a mathematical possibility explored on paper, not a particle any detector has ever actually captured or confirmed. Beyond the strange energy behavior, tachyons create a deeper problem tied directly to causality, the basic rule that causes happen before their effects. Because faster than light travel allows information to reach a destination before the light describing the original event could arrive, some physicists have shown that tachyons could theoretically be used to send signals backward in time, allowing an effect to arrive before its own cause. Causing something before the event that triggered it breaks nearly every foundation modern physics is built on. A red flag serious enough that most physicists consider tachyons far more likely to be a mathematical curiosity than a real, physical particle waiting to be discovered. Decades of experiments searching for tachyons, using particle accelerators and careful analysis of cosmic radiation, have found no evidence that they exist anywhere in the real universe. The overwhelming majority of physicists treat tachyons as a thought experiment, useful for testing the edges of relativity's equations rather than an actual population of particles racing invisibly around us. If tachyons remain firmly theoretical, another idea explores a completely different kind of shortcut, not breaking the speed limit itself, but bending the space light has to cross in the first place. Imagine folding a sheet of paper in half so that two dots drawn on opposite ends touch each other directly. A pencil could now punch straight through both dots at once, without ever travelling across the flattened distance between them on the unfolded page. Some physicists believe something similar might be possible for the fabric of space itself, a theoretical shortcut called a wormhole. A wormhole, according to Einstein's equations, would work as a tunnel connecting two distant points in space, potentially allowing something to travel between them without crossing the enormous distance separating those 2 points in ordinary unfolded space. Instead of light needing to cross 4 billion light-years the long way, a wormhole could theoretically connect the starting point and ending point directly, folding that distance down to something dramatically shorter. This idea comes directly from the same equations that describe black holes and gravitational time dilation, not from pure speculation with no foundation at all. The mathematics allows for solutions describing tunnels through space-time, connecting two separate regions, sometimes even two separate universes entirely, in theoretical models. This mathematical possibility comes with an enormous catch. Every known solution describing a stable, safely traversable wormhole requires a form of matter that has never been detected anywhere, matter with negative energy, propping the tunnel open and preventing it from collapsing the instant something tried to pass through. Picture a tent held up by poles pushing outward against the fabric. Ordinary matter behaves like fabric pulled inward by gravity, collapsing structures rather than holding them open. The theoretical negative energy needed for a stable wormhole would need to work like a pole pushing outward against the fabric of space itself, propping a tunnel open that gravity would otherwise crush instantly. Scientists have found tiny, laboratory-scale hints of negative energy in extremely specialized quantum experiments, nowhere near the scale or stability that a real, passable wormhole tunnel would require. Even if stable wormholes exist somewhere in the universe, they would not actually break light's speed limit the way a tachyon theoretically would. Light passing through a wormhole would still travel at its normal unbroken speed inside the tunnel. The shortcut comes from the tunnel itself connecting 2 points through folded space, not from light suddenly moving faster than usual. A photon using a wormhole shortcut would still experience its own permanent zero proper time along the way, arriving at a destination that simply required far less folded distance to reach. No wormhole has ever been directly observed anywhere in the universe. They remain a mathematically valid solution within Einstein's equations, explored seriously by physicists studying the outer edges of what spacetime might allow, without a shred of direct observational evidence confirming that one has ever actually formed. Whether through tachyons, wormholes, or any other theoretical shortcut, one truth remains unchanged across every serious idea physicists have proposed. Reaching light's true frame, its perfect zero distance and zero time, might require something entirely different from speed at all, something tied more closely to energy itself. Speed alone cannot buy a ticket to light's frozen frame of time. Energy is the real currency, and the price for even approaching that frame climbs so steeply that the entire remaining energy of a civilization would barely move the needle near the very end. Every earlier chapter about acceleration, about the Lorentz factor climbing toward infinity, about muons and satellites and astronauts, all point toward the same underlying truth. Getting closer to light speed does not cost a steady, predictable amount of energy for each additional bit of speed gained. It costs dramatically more energy for each small improvement. The closer an object already sits to the limit. Consider a spacecraft that has already reached 50% of light speed, an achievement no human-made object has ever come close to accomplishing. Pushing that same spacecraft from 50% to 75% of light speed would require roughly the same amount of additional energy as the entire first 50% took to achieve. Pushing further, from 99% toward 99.9%, would require an amount of energy dwarfing everything spent so far, just to gain that final, tiny sliver of speed. Picture climbing a staircase where each step grows taller than the last, gently at first, then dramatically, until eventually a single step towers higher than an entire building. Early progress up such a staircase feels manageable, even easy. Every step near the top demands an amount of effort that quickly becomes physically impossible for any climber, no matter how strong or well equipped. This energy problem explains why particle accelerators, some of the most powerful machines ever built by humanity, spanning miles of underground tunnels and consuming enormous amounts of electricity, can only push tiny particles to within a hair's width of light speed, never quite reaching it completely. It explains why interstellar travel at any meaningful fraction of light speed remains firmly in the realm of theoretical physics and science fiction, requiring energy sources far beyond anything currently available or even imaginable with today's understanding of physics. Photons never pay any of this steep climbing energy toll. Because they carry no mass, the energy required to keep them moving at light speed is not extra energy piled on top of some slower starting speed. It is simply the energy they are born with, already moving at full speed from their very first instant of existence, without any acceleration, without any staircase to climb at all. This split explains, in the clearest possible terms, why chasing light will always remain exactly that, a chase, never a catch. The energy price for closing that final gap does not grow steadily. It grows toward infinity, a wall built directly into the mathematics of the universe, rather than a limitation of current human engineering or ambition. If energy alone cannot close this final gap, one more question remains before this story reaches its own frozen edge. Even with unlimited acceleration and unlimited effort, what would actually happen to the traveller's own experienced time, pushed as close to the limit as the laws of physics will allow? A spacecraft with an engine powerful enough to accelerate forever, never running low on fuel, never needing to stop, would still never catch a beam of light. Time would bend more and more in the crew's favour the longer they pushed forward. The chase itself would never actually end. This connects directly to the Lorentz factor from several chapters ago. As a spacecraft's speed climbs closer and closer to light speed, time dilation grows more extreme, meaning the crew's own experienced time slows dramatically compared to everyone watching from Earth. A journey that takes thousands of years from an outside observer's point of view could feel like only a handful of years to a crew accelerating continuously at just the right rate, thanks to this shrinking effect on their own proper time. Physicists have actually calculated what this kind of trip would look like. A spacecraft accelerating at a comfortable, Earth-like level the entire journey, one that would feel like ordinary gravity to the crew on board, could theoretically reach the centre of our galaxy, a distance of about 26,000 light-years, within a crew member's own lifetime, experiencing only a couple of decades of aging inside the ship. Meanwhile, back on Earth, tens of thousands of years would have passed by the time any message could return. Picture a treadmill with a special property, where running faster stretches out the studio clock on the wall behind you, making it tick more and more slowly compared to your own steady heartbeat the harder and longer you run. No matter how fast or how long the runner pushes, the treadmill itself never lets them step off the belt and onto solid ground beyond it. The runner experiences less and less time passing compared to the room around them, gaining ground on the clock without ever fully outrunning the belt they remain trapped on. This means acceleration offers a genuine, real shortcut through time, without ever breaking light's absolute limit on speed. A sufficiently motivated crew, accelerating hard enough and long enough, really could cross the entire observable universe within a single human lifetime, according to their own onboard clocks, even though light itself would still need billions of years to complete that exact same journey from an outside point of view. The catch remains permanent and unbreakable. However close that cruise ship pushes toward light speed, however dramatically their own clock slows compared to Earth's, they never actually arrive at the zero time, zero distance frame that light itself lives in permanently. They can shrink their own experienced travel time down to nearly nothing. They can never erase it completely, the way a photon's travel time is already, permanently, erased from the very first instant of its existence. This gap between shrinking travel time towards zero and actually reaching zero explains something remarkable happening right now, tonight, every time you look up at a star. Look up at the night sky tonight, and some of the stars twinkling above you have already been dead for hundreds or even thousands of years. Their light is only now completing a journey that began long before you or possibly your entire country existed. Light travels fast, but the universe is enormous, and distance takes a real toll even at the fastest possible speed. The star Betelgeuse, a massive aging star visible in the winter sky, sits roughly 640 light-years from Earth. The light reaching your eyes tonight left that star around the time European sailors were still mapping the edges of unknown continents. If Betelgeuse exploded in a massive supernova at some point during those 640 years, nobody on Earth would know yet. The news, carried entirely by light, simply has not had time to arrive. This creates a strange, almost dizzying truth about looking up at the night sky. You are never looking at the universe as it exists right now. You're looking at a patchwork of different moments frozen in light, each star's light representing a different snapshot in time, layered together into a single sky. The moon's light left 8 minutes ago. Sunlight left the sun about the same 8 minutes. A star like Sirius sent its light about 8 years ago. Stars deeper in the galaxy sent theirs centuries or millennia ago. Some galaxies visible through powerful telescopes sent their light millions or even billions of years before Earth had formed at all. Picture a mailbox that receives letters written across enormous stretches of time, some mailed yesterday, some mailed centuries ago, all arriving in your mailbox on the very same morning. Opening each letter would reveal a message frozen at the exact moment it was written, with no way to know what has happened to the sender since then. The night sky works exactly the same way, an enormous mailbox filled with light, mailed across wildly different points in the past, all landing in your eyes during the very same glance upward. This delay means astronomers are, in a very real sense, historians rather than simple observers. Every telescope pointed at deep space functions like a time machine, capturing light old enough to reveal what distant objects looked like long before recorded history began, sometimes long before Earth itself existed. Studying the most distant galaxies detectable today means studying the universe as it looked shortly after the Big Bang itself, the same ancient light we explored several chapters ago as the cosmic microwave background. Every photon reaching your eyes tonight completed its own frozen, zero-time journey, exactly as photons always do. From your side of that journey, real centuries or millennia passed along the way, carrying real information about a moment that, for the star itself, might already be long over. If light alone always takes real time to cross real distance, one strange exception in modern physics seems to break that rule entirely, connecting two distant particles instantly, a phenomenon Einstein himself distrusted deeply. Two particles, created together and then separated by enormous distances, sometimes behave as though they remain secretly connected, as if measuring one instantly affects the other, regardless of how far apart they sit. Scientists call this quantum entanglement, and for decades it looked like it might finally be the loophole that lets something outrace light after all. It is not. Entangled particles share a strange linked relationship from the moment they are created. Measure a property of one entangled particle, and the matching property of its distant partner becomes instantly determined, even if that partner sits on the opposite side of the galaxy. Einstein himself distrusted this idea deeply, calling it spooky action at a distance, worried that it might violate his own speed limit by transmitting an effect faster than light could ever travel. Decades of careful experiments have confirmed that entanglement is real, not a trick of measurement or a flaw in the mathematics. Physicists have entangled particles and separated them by tens of miles, confirming the connection holds even across that distance, with results matching quantum theory's predictions precisely. The tempting conclusion that this proves faster than light communication is possible turns out to be a misunderstanding of what entanglement actually allows. Here is the crucial catch. Measuring an entangled particle produces a completely random result, not a result either scientist can control or predict in advance. One scientist measuring their particle has no way to send a chosen message to the other scientist, because the outcome of their own measurement is pure chance, decided the instant they measure it, not decided in advance by anyone. Comparing results and confirming the connection still requires sending information the ordinary way, through a phone call, an email, or a radio signal, all of which travel at or below the speed of light. Picture 2 sealed envelopes mailed to opposite ends of the country, each containing a card that says either heads or tails, guaranteed to match each other perfectly, though nobody knows which one until an envelope gets opened. Opening one envelope instantly reveals what the other envelope must contain, without anyone actually sending information between the two locations at the moment either envelope gets opened. The correlation existed the entire time, built in from the very beginning, not transmitted in that instant. Quantum entanglement reveals something genuinely strange and important about the deep structure of reality, a connection between particles that does not fit comfortably into ordinary, everyday intuition. It offers no shortcut around light's absolute speed limit, no secret backdoor for sending usable information faster than any photon could carry it. Every attempt to use entanglement for faster-than-light communication has failed, exactly as relativity predicts it always must. Light's limit survives this challenge completely intact, standing as one of the most thoroughly tested, unbroken rules in all of physics, guarding the frozen, timeless frame that only photons themselves are ever allowed to occupy. The oldest light in the universe carries a secret that flips ordinary logic completely upside down. The photons that have travelled the longest, existing since almost the very beginning of everything, are, in a strange and very real sense, the youngest travellers the universe has ever produced. This connects every idea from this entire story into one final unified picture. Every photon experiences zero proper time, frozen permanently from the instant of its creation. Age, in any meaningful sense that applies to a person or an object with mass, requires time to actually pass. A person ages because years tick by on their own internal clock, cells dividing, memories accumulating, moments stacking up one after another. A photon's internal clock never ticks at all. Not once, not ever, no matter how many billions of years it spends crossing the universe from an outside point of view. The cosmic microwave background, the ancient light released when the universe first became transparent nearly 14 billion years ago, therefore exists in a strange dual state. Judged by how long it has been travelling through the universe, it ranks among the oldest things science has ever detected, a fossil preserving conditions from almost the dawn of time itself. Judged by its own frozen internal relationship with time, it has aged exactly 0 seconds since the instant it was born, making it, by that measure, permanently new. Picture a letter sealed inside a time capsule the day it was written, then opened exactly 100 years later. The letter itself has existed for an entire century, aging alongside everything else in the world around it, the paper yellowing, the ink fading slightly. Now imagine a different kind of letter, one that somehow avoided all of that change entirely, arriving a century later in the exact same condition as the moment it was sealed, its message perfectly preserved, untouched by the passing decades. A photon works like that second impossible letter, existing across enormous stretches of outside time while remaining completely unchanged, completely unaged in its own frame. This paradox, ancient by outside measurement and eternally new by its own internal experience, applies equally to every single photon in the universe, not just the oldest ones. The light leaving a lamp in your room right now shares this exact same frozen youth with the ancient light from the early universe. Neither one experiences the passage of time that separates their vastly different outside ages. Nothing in daily human experience prepares anyone for a concept like this, something that gets older by every outside measurement, while staying permanently, eternally new by its own internal clock. Light lives in a category entirely its own, untouched by the aging process that governs literally everything else that has ever existed with mass. This strange, doubled relationship with time reaches its most personal, most emotional edge in one final scenario, a message sent across the stars at light speed, and the two very different experiences waiting on either end of that impossible journey. Imagine sending a single beam of light carrying a message toward a planet orbiting a star 4 light-years away, the nearest star system beyond our own sun. The message leaves Earth in an instant, from your own point of view. 4 years later, someone standing on that distant planet finally receives it. For the beam of light itself, carrying your exact words across that entire distance, no time passed at all. This final scenario pulls together every idea explored throughout this story into one deeply personal picture. You, standing on Earth, experience 4 full years passing while your message crosses the gap between stars, years filled with birthdays, seasons changing, an entire chunk of your own life lived out while your words are still technically in transit. The person receiving your message on the other end also experiences real time passing, waiting, wondering, living their own 4 years of life before your words finally arrive. The light itself experiences none of this waiting. From the message's own impossible point of view, if such a point of view could exist and be described, it left your hand and arrived at its destination in the exact same instant. 0 seconds passing, 0 distance crossed, exactly as every photon in this entire story has demonstrated. Picture writing a letter to a friend serving on a research station in Antarctica, sealing it inside a bottle and setting it adrift in a very slow, very patient ocean current that happens to know exactly where to go. Months might pass before that bottle finally washes ashore near your friend's station. The letter itself, sealed inside glass, does not experience the drifting months the way you and your friend both experience the waiting on either end. A beam of light crossing space works similarly, though far more extreme, sitting completely outside the flow of time that governs everyone anxiously waiting on either side of the conversation. This creates a strange kind of asymmetry built directly into the universe. 2 people separated by light years can never have a real-time conversation, no matter how advanced their technology becomes, because the light carrying their words remains bound by the same limit as every other photon in this story. A question sent today would not receive an answer for at least 8 years, 4 years for the question to arrive, 4 more for the answer to return, an entire conversation stretched across nearly a decade of 2 separate lives, while the light itself, carrying every word both ways, experiences none of that waiting whatsoever. Every message ever sent between stars, real or imagined, will always work this way. The senders and receivers age. They wait. They live entire chapters of their lives between question and answer. The messenger itself, light, remains forever exempt from that wait, forever frozen at 0, carrying real information across real distance while somehow experiencing neither. This asymmetry between everyone who waits and the one thing that never does leads to one final, unsettling question that has quietly challenged physicists for over a century. After exploring every equation, every experiment and every strange consequence of light's frozen relationship with time, a surprising number of physicists argue that the very question this entire story has been built around may not actually make sense at all. What does a photon experience? Some experts believe that question breaks down completely the moment you try to answer it seriously. The trouble starts with a basic requirement hiding inside the word experience itself. Having an experience, in every case physicists can actually test and describe, requires some flow of time passing, moments unfolding one after another, a before and an after connected by something in between. A photon's proper time sits locked at exactly 0, meaning there is no before and after inside its own frame at all. Without any flow of time whatsoever, many physicists argue there is nothing left for an experience to happen within. The same way a story cannot unfold without any pages to write it on. This does not mean physicists consider the earlier chapters of this story wrong or misleading. Every calculation showing that photons experience 0 proper time and 0 distance remains completely accurate, confirmed by the same mathematics that predicts muons, GPS corrections, and astronaut aging with remarkable precision. The disagreement centers on a much subtler point, whether describing that 0 as an experience, something a photon lives through, even in some frozen or instantaneous way, stretches language and imagination past what the physics itself actually supports. Picture asking what color silence sounds like. The question uses ordinary words correctly, combining silence and sound and color in a normal, grammatically sound sentence. The concept underneath the words falls apart the moment you examine it closely, because silence exists specifically as an absence of sound, meaning asking about its sound quality mixes categories that were never meant to combine. Some physicists believe asking about a photon's experience commits a similar category mistake, borrowing a word, experience, that was built entirely around the assumption of time passing, then applying it to the one thing in the universe explicitly defined by having no time pass at all. Other physicists take a gentler position, arguing that talking about a photon's frame, even in frame with zero duration and zero distance, still offers genuine insight into the deep structure of relativity, useful as a limiting case even if it cannot be described as a true, felt experience the way a human moment can be described. Both camps agree completely on every underlying equation and every confirmed experimental result. They simply disagree about how far human language and imagination can stretch to describe a frame of reference that mathematics allows, but ordinary intuition was never built to hold. This disagreement does not weaken anything this story has explored. It reveals something rarer and more interesting. A genuine edge where physics keeps working perfectly, producing precise, testable, repeatedly confirmed numbers, while human language quietly runs out of road entirely. Every idea in this story points toward the same picture, painted from 100 different angles. Somewhere underneath the sun warming your skin, underneath the ancient light still arriving from the birth of the universe, underneath every star scattered across the night sky, light itself stands permanently still in time while everything else keeps racing forward. A photon leaves its source and arrives at its destination in the same frozen instant, no matter whether that trip spans a few feet across a room or 14 billion years across the entire visible universe. Mass is the price every other object in the universe pays for the ability to stand still at all, a price photons never had to pay and can never afford even if they wanted to. Time bends around speed and gravity for everything that carries mass, stretching gently for airplanes and satellites, dramatically for astronauts and muons, and almost to the breaking point at the edge of a black hole. For light itself, time does not simply bend, it stops entirely, locked at zero from the very first instant any photon comes into being. Every star visible tonight sits frozen in its own version of the past, its light carrying a message written years, centuries or millions of years ago, arriving fresh in your eyes at this exact moment regardless of how long ago it actually began that journey. The oldest light humanity has ever detected, the cosmic microwave background, remains simultaneously the most ancient and the most eternally new thing the universe has ever produced, a paradox that only makes sense once you understand exactly what this story has spent its entire length building toward. Picture standing at the edge of a perfectly still lake at night, watching stars reflected on water so calm it looks frozen in place, while somewhere beneath the surface, fish and currents keep moving constantly, invisible beneath that stillness. The universe works a little like that lake. On the surface, wherever light exists, everything sits permanently, eternally still in time. Beneath that stillness, everything else, planets, stars, galaxies, and every person who has ever lived, keeps moving, aging, racing forward through time that light itself will never have to cross. This is the strange, quiet truth hiding behind every sunrise, every star, every beam of light that has ever touched your eyes. You have spent your entire life surrounded by something that experiences absolutely none of the time you experience every single day. A universe built from countless frozen instants, all moving at the one true speed limit that everything else can only chase. Next time you look up at a clear night sky, remember what you are actually seeing, not simply stars. Frozen messages, arriving after impossible journeys, carried by something that has never once felt the passage of time at all.